Hello, this is video number 29, and we're still looking at trees. Specifically, we're still looking at binary search trees. Binary search trees are so much fun, aren't they? Let's just do another one, just for the heck of it. So let's build a BST using these keys. I went ahead and wrote those in advance so that you wouldn't have to watch me write them down, and also so I could make them nice and neat and legible. That's about as good as my handwriting's ever going to get. I hope that font size is large enough for you. But let's build a BST, shall we? A, insert A, that will be the root. And I'm just going to show the internal nodes, and might not even, yeah, I'll put boxes on them, why not? That's A in a root all by itself. B is greater than A, so it will go off to the right. Next one is Z, A. We always start at the root comparing, of course. Our recursive descent through the tree will find the location, and we'll be replacing an external node with an internal node. You know all that. So here we go. B and then Z. Y. Y is greater than A, greater than B, but it's less than Z, so it will come back to the left from Z. Then C. C is greater than A and greater than B, but it's less than Z and less than Y, so it will be to the left of Y. X. X is greater than A and greater than B. X is less than Z. X is less than Y, but X is greater than C. So X will become the right child of C. And then W. W is greater than A, greater than B. W is less than Z. W, X, Y. It's less than Y, but greater than C. WX. It's less than X, so it will come to the left of X. I hope I'm not putting these in the wrong order. V. V is greater than A, greater than B, less than Z, less than Y, greater than C. UV, WX, UV is less than X. UVW is less than W. So it comes over this direction. Comes to the left of W. U. U is greater than A, greater than B, less than Z, less than Y, greater than C. UV less than X. UVW less than W. UV less than V. So it becomes the left child of V. And finally D. D is greater than A, greater than B, less than Z, less than Y, but it's greater than C, but it's less than X and way less than all the rest of this stuff, so it's the left child of U. Parity check, inserting keys 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now then, let's pause and reflect on this binary search tree that we have here. And if I'm standing in front of the whiteboard, I'm sorry, but Solomon is right here, pretending he's a rug under my feet, and I'm going to stumble over him, sure as the day. What do you notice about this binary search tree? Okay, you've had plenty of time. It has degenerated. It's not strictly a linked list. It's not all right child or all left children. But look at this. Depending on the order of insertions, we could very well get a binary search tree that has degenerated to where we no longer have, if you recall these terms, order log, that's LG log base 2 of n. That was the smart contestant playing The Price is Right that would go higher, lower, and zero in on it. That's what our binary search tree data structure is all about, is so that we get cool order log base 2 of n searches without having to look through everything. We've lost it here. These are not going to be log base 2 of n. These are going to be order n. Which means, if current trends continue, if we have twice as many nodes and they're all strung out like this, it's going to take us twice as long to do the searches. So that's a problem. That's a problem. That is a problem with BSTs. Problem. It's always nice when problems have solutions. Solution? S-O-L-U-T-I-O-N. I'm distracted by my barking dog. Everything's a distraction today. But Solomon moved. Yay. Solution, use a balanced tree. B-A-L-A-N-C-E-D, tree. A term for these things that I like even better, it sounds like robots, automatic, all that stuff, or also known as A self-balancing tree. The tree knows how to balance itself. Self-balancing tree. Sounds cool, doesn't it? It is cool. I can't wait, but I'm going to have to because I filled up the whiteboard now. And all this will be gone except for the keys. I want to keep the same keys and see if we can improve on the structure of the data of our dictionary for this. So that's it for this one. I'll see you online.